Hello everyone, this is Akhil Reddy Cherukupalli. I have chosen the topic Clio, a hardware software co-designed disaggregated memory system. Clio hardware. It includes a new virtual memory system and it is also like a customized network system, and it also uses a framework for computation offloading. So in this Clio building, we not only co-design its functionalities, hardware architecture and network system, but also design the computing nodes and memory nodes. So we included FPGA prototype in the Clio to demonstrate like each memory node can achieve 100 Gbps micro second level average, and it has like tail latency for the terabytes of hardware. So for these we have like these research questions, we include some of the categories in it. So by achieving all these possibilities, we use to eliminate its state from the MN hardware. So in this, the MN can treat like each of its incoming requests in isolation, even if the requests that the client issues can sometimes be interdependent, and it doesn't store the metadata or else deals with it. So without remembering any requests in it, it has also like saving the monetary and energy cost, and it has achieving the great scalability in it. So without the state, the hardware pipeline, it can be made by smooth and performance deterministic only. Goals like to keep the number of memory devices and the total cost of a cluster low. Each MN should host like hundreds of GBs to a few terabytes of memory, so it is hosting the large amount of memory. And then so for this new memory hierarchy, disaggregated memory is larger and maybe slower than the local memory, but it's still faster than its storage. So the memory disaggregation is a network based, and it has to match the state of the work like network speed, that is 100 Gbps throughput. We allow the low latency and the high throughput in it. And for the memory accesses, we need to prevent like malicious clients from the reading or writing memory operations at MNs. We should not allow any direct access in it, so the memory should be protected. And the flexible, so the memory disaggregation, it should always be flexible, like for supporting like any high level languages of API, or to offload any application logics, and to incorporate different network transports. And for the low cost, it's like the cost should be like it'll be low. So if it has like any low cost, it should use like expensive hardware to build MNs, and it consumes huge energy, and it also costs more at computer networks than the cost saved at the MNs multi networks. So this is the Clio architecture, and these on the left side we can see the CNs, which are regular servers, and it is also equipped with the Ethernet, and it is also connected to the top of rack 2 or switch. And then it's like it is also like it's main like customized devices, it is connected through the switch. And then applications which runs in the CNs, we can see on the top of the in that consists of like C library. They are like RLOC free or read write and extend API operations, and there are charges of like request ordering, congestion control, and request retry. And then which comes to the MNs, it is a Clio, and it has a like C board, and it consists of like many of like data accesses, which is a prototype with the mainly with the FGPA. And it has also a ARM processor which runs the software, and it also handles the metadata and controls the operations. We can see the slow path operations over there on the top, like VALOC and PALOC. And then it has also host application computation offloading with the extended path, the offload path. The Ethernet is connect, we can see the Ethernet arrow towards the offload extended path. And then like after getting the incoming request, and it travels through the Ethernet physical and the MAC layers, which is known as MAT, match and action table. It decides the three paths, like where it should like where should it go. And then after the request is stays in the ASIC, and it goes through a hardware based virtual memory system, and it performs the tasks in the pipeline like translation, permission checking, and page fault handling. Challenges. So the first one is like hardware pipeline should be deterministic and smooth. It is because by using like a known number of cycles to process a data unit, for each cycle pipeline can take a new data unit. So the before the previous one, the former, it should ensure like a low latency, because the later it should guarantee a throughput that could not match the network line rate. And then like for example, the traditional CPU pipelines could, it has like stalls because of the data hazards and of like non-deterministic latency, to like to it can't handle the memory instructions. So to challenge these, like we have, they issued the challenges, and they approached a new technology like technique like a Clio virtual memory system, with the like having following principles to eliminate these like kind of states and challenges. And the other challenge is like data buffers and metadata, that the hardware users should be minimal and have bounded sizes. So in these like traditional software, it approaches normally the various data buffers and the metadata, because of like they are large and grow with the increasing scale. And according to like today's reliable network transports, it maintains like a sequence number per every connection, and the buffer, it has like unacknowledged packets for the packet ordering and retransmission. And also again I would like to include like swapping between the on chip and off chip, the memory is possible, but if we do so, it would like increase like the tail latency and the hardware logic complexity, especially because of under the like large scale. Principles. The first one is avoid state whenever possible. So like not all state in the server based solutions are necessary. Like if we can redesign the hardware, like RDMS MR indirection and its metadata altogether by directly mapping application processes, we can see in the Clio architecture that should can be possible. And the other one is shifting functionalities and states to CN. So in the hardware resources, the scale is like at MNs. So CNs have like sufficient memory and processing power. So as it goes faster to develop the functionalities in the software, it has like a solution to shift its states and functionalities from MNs to CN. So there is like how much and what to shift, like what all things need to be shifted. So to shift the functionalities to CNs, only we can do it by have like to reduce the hardware resource consumption, and it doesn't slow down the common foreground data operations, so basically like data operations, and it does not sacrifice the security guarantees, and it should add like memory space to it. So as like it, the shift may result in like uncommon operations like handling a failed request, and it becomes very slow. As we discussed in the Clio architecture, they introduced the three areas as the green, yellow and red, with the ASIC and FPGA and the low power cores. They included the slow path, fast path by its own operations, and finally they are connected to the DRAM, which has a hash page table, sorry, we can see it. And they conclude by performing the operations separately by using the VI location over there in the top. So in this slide we can see the latency and the goodput bar charts over here by including the all operations, read and write operations, and the Clio based operations, and also the RDMA operations in it. We can see the top one as the latency and the bottom one as the goodput, where we discussed previously like to increase the 100 Gbps and the 2.7 times of the latency. They're produced with the process scalability and the PT and MR scalability, and they also compared with the page fault and the TLB miss rate, and then finally by including the latency over there. And then for the goodput, they have like end to end and in the onboard, in the ongoing operation, and then the read latency, and then also finally write latency problem. So the memory disaggregation, it's like based on a hardware, and it provides the appropriate amount of computing power at memory nodes. So we'll be concluding with three different type of hardwares for this problem, and we're gonna decide how it gonna be processes. Related work, it includes a virtual memory system and has a specialized network system, and it has also a like compute offloading, all these included in the Clio hardware. So we do like co-design like the features of the operating system and the hardware architecture, and there from that network system we can like develop the Clio architecture, but we can also co-design the computer nodes and the memory nodes in the Clio architecture by using different type of hardwares in it. Authors solve this problem by introducing the virtual memory system and having like a computation offloading by including the three components which make the Clio hardware, and they find that the tail latency is much lower than RDMA, and it is 2.7 times quicker than the solutions that SmartNIC has to offer, and they also included these three parts linked to one another in a way. Experiment. So the authors in this research, they conducted a text experiment of by including different softwares to come up which is the best one. So this research is mainly on the memory disaggregation, and it has a lot of advantages by providing like more effective use of the memory and making the administration easier by including different type of hardwares in it. Results. So the Clio is as like discovered responsible for performing the permission operations like in MNs and the computer networks, and basically by providing the authenticity of process IDs is essential to the protection of Clio by letting like a trusted computer network operating system and its hardware by attaching its process IDs.
Improvement. So offloading the software stack to the specialized software, it could allow like Clio's performance to be improved, and then it also be beneficial for the Clio. And then our current implementation contains designs, it could be improved by increasing the protection against the side channel and DOS attacks, and also like increasing the amount of isolation present in these components could result in like either increase in the cost of the C board or else decrease in its overall performance. Reference for the paper. Thank you everyone. If you have any questions, please let me know in the discussion section.